Hey everybody, let me about to hear double audio. Ready? There we go. Double audio fixed. We'll start doing some work right here. If you join in, feel free to ask a question. I'm gonna do some of the questions that are pretty hard on chapter 14. So let's just jump into it. Here we are, some chapter 14, so people can check this out later. We'll go right here. 7-point curve. What? There we go. Hey, what's up, Braden? I was wanting to ask you if you could explain model hierarchy and how to determine which is maintained. Yeah, sure. Let's do that. Great question. So let's do some model hierarchy right here. Got a whole bunch of stuff. So when we're looking at model hierarchy, let's consider what model hierarchy is. I think we have GPA. So let me show you what model hierarchy is. We'll be talking about that a little bit in class today. Or if you're in class yesterday, we mentioned it, but let's go over that. Thank you so much for being here, Braden. Great question. Let's go right here. Let's load in some data, and let's talk about what model hierarchy is. So what is model hierarchy? That's how it's spelled, right? No, it's not. I can never spell this word. I do not teach spelling. They should have a spell check in this now. Okay, so when we talk about model hierarchy, the best way to think about model hierarchy is the following. If we have the interaction between two variables, which we see up here, here's the interaction between two variables. We need to include in the model the two variables themselves. These are sometimes called the main effects or the lower order terms, but do you see here how we have weight and we have GPA? A model that would not carry through model hierarchy would look like the following. So why does this model, Braden, right here, not carry model hierarchy, which is something we generally want to do? It's a good idea, like for models that have interactions, because we're saying that one variable is going to explain another, like the way in which this variable x1 is explained depends on x2. So we can talk about an interaction here in a moment. But why does this not carry out model hierarchy? And I'll do a drawing here that might help, where the previous one does carry model hierarchy. I can get them both on the screen if I make them smaller. So we can see right here, this model down low does not carry model hierarchy, where this model up here does carry model hierarchy. So this one does carry model hierarchy, and this one down low does not carry model hierarchy. So if you notice, the term right here is x1, x2, and let's kind of draw this out right here. We'll take a screenshot of this, and I'm going to cancel, and so we can not have it highlighted. And let's put them both on the screen right here and talk about this output and think about why. Because it doesn't show pretty much. No, you're on the right track, Braden. That's it sounds more complicated than it is. This model up top, and hopefully this will help make sense of it, and this is great to put in a video. So Braden, thank you so much for being here and asking this. Exactly the point of office hours. This model, if we think of this as x1, like this is just x1, this is x2, this is the x1, x2 interaction. This over here is the x1, x2 interaction, but it does not carry through model hierarchy. And I want us to think about what model hierarchy might look like. Model hierarchy probably, if we draw it out, would look like a tower. So if you think about the way a tower would work, a tower, you have to build up the tower to get to the top of it. So we're going to erase everything in here and draw a hypothetical tower. So let's erase all this, and let's draw a tower. So the way in which we use model hierarchy is the following. This is really good, just understanding of model hierarchy that we can draw out here. When we think of model hierarchy, if we have a tower that goes to x1, x2 interaction, what do we need in our model to get to the x1, x2 interaction? To get to the x1, x2 in the x1, x2 interaction, because this model does carry model hierarchy, and this model down low does not carry model hierarchy. So this is currently we're displaying this one right here that does not carry model hierarchy. So the one we're currently displaying is this, the way this is set up. So this one does not carry model hierarchy. So since this one does not carry model hierarchy, you'll notice, what about it? And then how would we carry out model hierarchy? How would we carry model hierarchy for this? So what is different about this? And you think about building a tower, if you have the x1, x2 interaction, what do you have to have? I might take the phone off. If you have the x1, x2 interaction, what would you have to have? If you have the x1, x2 interaction, which is, we'll zoom in on it here. The x1, x2 interaction is this up here. Right now we're displaying it this way, though, where we do not carry model hierarchy. So, oh, no, that's fine, that's fine. So right now it looks like this. Don't worry. This is great questions. Like keep asking, Braden. This is the kind of questions, like, just be like, I don't know. That's perfectly fine to say. Do not worry. I'm gonna throw some 20 points out there. Do not worry. A perfectly fine answer is, I don't know. That's perfectly fine. So what you'll notice right here is, and these x's right here are not x variables. We're missing these. Does this make sense? Like right now, the way I've drawn this, we have here x1 and x2 are in the model. Do you see here this is x1, x2? Does that make sense right here? We have x1, x2 interaction in the model, but we don't have what in the model where this one does. Like this model does not carry model hierarchy. That's why I've got the x here saying that's an x, like it does not meet model hierarchy, and this one does meet model hierarchy. Does this... this means we're multiplying them together. That means interaction between the two variables. So, and great questions, Brain. Yeah, feel free to ask anything. Like, what does that mean? This means the interaction between. So that's why what I wrote right here. This is like the first x variable and the second x variable. That's exactly why it does not carry out model hierarchy. Which you can break model hierarchy. It's just model hierarchy says if you have the x1, x2 interaction to maintain model hierarchy, which we do up there, you need to include in your model x1, x2. The same thing works for polynomials. If you have, let's say, and I'll bring up the slides here in a second on this, I think they also showed pretty well. If you have a polynomial model that goes all the way up to the 5th power, to maintain model hierarchy, you'd have to include x4, x3. It's like all the lower order terms, we call them sometimes, and you have to include the linear term. So if you had a model that built all the way up to the 5th order polynomial on an x variable, you'd have to include all the lower order polynomials. Does that make sense there? That like if you do a 5th order polynomial, you need to carry through the 4th, the 3rd, the 2nd, the 1st order polynomial terms. Yeah, exactly. Yeah, Braden, you're getting it right there. Like to meet model hierarchy, you need to carry through all the things that would make it. So let's say, let me ask you this. Let's make a crazier model with really bigger model hierarchy. I think desired weight is a variable in this. Hint, this will carry through model hierarchy. Desired weight. I did spell it correctly. Does this carry model hierarchy or not? Does this carry model hierarchy or not? Are the coefficients in this model carrying model hierarchy or not? And this one's more complex. This is, like sometimes we put a tougher one on the test. This would be a little bit tougher now. What you want to look at is the highest order interaction. Right now, you could classify this like, try to think about what I'm going to write right here, how I would describe this without naming the variables. I would say that's an interaction between blank, blank, blank. So that's an interaction right there. That is the interaction term between this. And don't use variable names. I mean, we should if we're explaining it to someone, but just in the general term, that is the interaction between blank, 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 like without variable names included. So just think about it like I was doing general terms before. Because you have different, like, here's a hint. This is x1 right here. This is x2. So, and then you can actually see down there what it is. You can see that is the interaction between x1, x2, x3. Does that make sense? Like this is the interaction between x1. And these are just being multiplied. It uses a colon, but that is the interaction between those. Building blocks, exactly. That's the way to think about it. Like the polynomials are just built on the one variable itself, but the interactions are built on the other ones. So the way this one looks is more complicated because we're actually carrying through model hierarchy here, because what do you notice about this? This is the interaction between x1, x2. This is the interaction between x1, x3. This is the interaction between x2, x3. So these are all the subsequent building blocks of lower order interactions and single order terms that lead up to the three-way interaction. That's the term I was looking for. Not third degree polynomial, but three-way interaction, like three variables interacting a third way. Is the third polynomial all three of the interactions? So this wouldn't be polynomial right here. Polynomial allows us to make bends in the model. Interactions allows us to make like a it depends model. So when we talk about interactions, then the way x1 impacts x2 depends on, or excuse me, the way x1 explains y depends on x2. Sorry, switching topics right there. So this is how interactions look, and the other one is polynomials. So here, let me label these right here. We'll go black pen right here. So this is polynomial models. Sure, that's black pen. If you can't tell. This would be polynomial. And this is how interactions generally look. Interactions are going to change the slope of the... So an interaction changes the slope of the line, where a polynomial allows for additional bends. Does that make sense what polynomials will do? Polynomials allow the model to do a nonlinear fit, where interactions allow models to change the coefficient depending on another variable. So we might have, and I can show you examples of this if you want. Just your office hours right now, you're here, you're asking the questions, just direct the conversation. Say, Brian, go into more detail on interactions. We won't really examine a three-way interaction. Those are very hard to graph and very complex to say. The way in which x1 explains y depends on x2, but the way in which x2 impacts x1, which explains y, depends on x3, because there's a three-way interaction right there, and it's not statistically significant, so we should probably exclude it from the model. I just kind of threw it in there. This model has very little significance right now, probably due to multicollinearity. What topic would you like to hear about? Feel free to ask. It is your choice. Go into more detail on polynomial, interactions, and you're probably starting, can you show an example with the variables, difference between a polynomial? Yeah, sure. So polynomials, the best way to think about a polynomial model is you're just fitting a parabola if you just go second degree polynomial. And do we have ways of graphing that? I might have to not use our stuff to graph it. I might have to use a different program, like a different code. When you do a polynomial, actually we can look at it this way. We can view the polynomial. We do have a way of doing it. I don't think visualize model will visualize a polynomial. Let me vanish. The choose order function allows you to investigate polynomial trends in models. And here's a really important skill set. So this is using the choose order. I'm going to do a cut in the video right now. Okay, so this is how to use the choose order. This is how to read the output. This is very important for the test. So putting a cut in the video, future Brian, so you remember this. I do this so I can change topics, and here we go back to it. Let's do it. Okay, so reading this output right here, we have 3 steps. Let's write down the 3 steps for doing it. The 3 steps for reading this output are: step 1, find the highest r squared adjusted. So we're going to find the highest r squared adjusted. Step 1. Step 2, subtract 0.005 from it. Step 3, start with order 1 and see if it meets this standard. Continue until a model meets this standard. Okay, let's do the first step right here. You ready? First step. What is the highest r squared adjusted? Which order has the highest r squared adjusted? So first, and then we're going to think about the polynomial, what it means. And then we're going to talk about model hierarchy with that a little bit here. So which one of these is the best? Which one of these is the best? Oh, it's going to be so interesting. Which has the highest r squared adjusted? Correct. So what we're going to do is we're going to take this right here, and then we're going to do what to it? What do we do once we identify the best? We do what? Don't worry, this is your practice too. I don't know it's on the screen, but I'm going to take that number right there, and I'm going to do what to it? It's like the practice. So if you're watching this, make sure you be like, okay, I need to do that. I'm not going to say it. I want you to say it. I want you to practice it. I want you to write it down. I want you to be like, okay, I found the highest r squared adjusted, and then I do this to it, because I'm going to do that here in just a second. I'll start doing it while we're typing it in. So I'm going to take it, and then I'm going to subtract. No, we're just going to subtract this right here. So the whole point of this is, let me put this. I'll explain why we're doing this, because maybe the why would help. Which polynomial order from choose order will we use? So the question we are asking is, which polynomial from the choose order will we use? So that's what we're investigating right now, is like, which polynomial order will we use? Does that make sense? We're going to find the highest R squared adjusted, which we found right here to be this. This was the highest. And so we found the highest. And now we're going to subtract 0.005 from it, which is a very small amount to subtract. But we're going to like take a little bit off of it to see if like, just be like, well, within this would be okay. But we're going to subtract just a little bit off of it. Does that make sense? Like, we are just taking a little bit off of it to be like, well, let's lower it just a little bit here. So this is step 1, and this is step 2. Yep. Great job, Braden. Just keep asking questions. Anything doesn't make sense, just let me know. And so here is what we get. Okay, now which model am I going to start with? Just put a number in the chat. Which model am I going to start checking to see if it meets this standard? This is how much I have to get for my R squared adjusted for it to be good, like to be a model I'm going to use. So we have to meet that standard. During these office hours, could you go in more depth on central? Yes, Emily, you got it. You bet. We'll do it right after this. You got it, Emily. I'm glad to help out. So you're here. You got it, Braden. We'll start here with model 1. Does it meet that standard? So I'll let you do the first one, then I'll do the next ones. We look at this standard and we say, does this meet the standard? Does this right here meet the standard of this? It needs to be at least that. So does this right here, this value, meet this standard? Yes or no? And I'll do the next. That kind of gives it away if I'm saying I'll do the next one. I will do the next one. That gives it away. No, it's too low, exactly. This one does not, this one does not, and this one does. What do I mean by it does? It's the first one that's over the standard. Our goal here is to use a simple model. Like, that's why we don't just go to the sixth degree polynomial. We're going for, like, this model is pretty much as good, but it's a little bit simpler. And I want you to notice about the 4th, the 5th, and the 6th degree polynomial in this graphic. Do you see how the 4th, 5th, and 6th degree polynomial, might have been good if we did that. No, what are you doing, graphic? The 4th, 5th, and 6th degree polynomial all kind of overlap. Does that make sense how they're all kind of overlapping right here? The 2nd and 3rd kind of overlap, and look at their R squareds adjusted. The 2nd and 3rds are very similar. The line sticks out like a sore thumb, and it's got a worse R squared adjusted than all of them. But the 4th, the 5th, and the 6th, which are these bluish and purple lines right here, they're all kind of interwoven really tight. And they are a little bit similar to the other ones, but these start to break away on certain portions where these have additional bends. But it looks like the addition of the 4th, 5th, or the 5th and 6th bends in the polynomial, because it gives additional bends, aren't really adding much. Like, they're not really helping. And that's why we're saying, well, the 4th degree polynomial is probably good enough. Does that make sense? Like, the 4th degree polynomial, good enough. Like, does this make sense by the theory behind it, Braden, like why we're doing this? We're going for the best one, and then we're seeing if we have one that's basically as good as it. Because when you look at these models right here, these blue ones, yep, they're like, they're all basically the same. So let's go with the simpler one. It's kind of Occam's razor. Like, they have the same explanatory power, two things of equal explanatory power. We should probably use the simple one, because it's like, we could take 10 trips to get to the mall, 10 turns to get to the mall, or 2 turns to get to the mall. And the 2-turn way takes about 10 seconds more. You're like, well, basically the same. Let's just go the 2-turn way. It's a lot simpler of a path. Takes a tiny bit longer, but we'll take it for the simplicity. So then how do we build this model? Well, we're going to take this model we already have and kind of adjust it by taking the weight variable and putting it inside of the poly function. So the poly function allows us to raise things to a polynomial degree, and let's call this m poly. And that creates the poly model right there. So the function poly right here creates polynomials, and I'm 99% sure it carries through model hierarchy. We'll find out the hard way if it carries model hierarchy or not. It does. How do I know this carries out model hierarchy? This goes back to the idea we were talking about earlier. How do I know this carries out model hierarchy right here? Why does this, and it's almost exactly what we did here when I did a 5th degree polynomial. So Braden, review question now. Why does Brian's, oh no, it's going to erase that no matter what I do because I can't get it. Oh, I did it. Why does this output right here, where I did the 4th degree polynomial, carry through model hierarchy? So why does this carry model hierarchy with this 4th degree polynomial? And so we did the 4th degree polynomial, and so that's the one we're doing. And why are we keeping model hierarchy? Which I might have a hard time removing it. I've never tried to remove polynomial model hierarchy. So why is model hierarchy maintained in this example? This is really good. Like, we talked about model hierarchy with interactions, model hierarchy with polynomials. So really good. I think once you see it, you're like, oh, you just got to do this. Like, why is the model hierarchy maintained? And the answer is in this right here. So it lets me highlight it. Okay, so the polynomial is the same as just range for the power necessarily. Exactly. Yes, that's exactly it. So polynomials are different than interactions because polynomials allow for bends in the model, where interactions allow for, like here, I'll make an interaction model so you can see what an interaction model looks like. So you see polynomials allow like additional bends, and by carrying through lower order polynomials, we are carrying model hierarchy. So the fact that we're doing the fourth, but we have the third, I don't know how to do things. But by carrying out from the fourth down through these, this is the carrying model hierarchy part of it. So you just have to think about like, okay, we have the fourth order polynomial. We have to carry through the lower order polynomials to carry model hierarchy. So that is in this output right here. You can see the fourth order polynomial was used, and then the lower polynomials were also carried through. This is not the model anymore that we're building. It's showing the different polynomials. I don't even know if we can visualize our model properly. Wait a minute. It's carrying through the other polynomial terms. And we do get significance, which is good. The way interactions look, let's make an interaction model, and then Emily will do your question. Great question. Interactions are going to look a little different when you have a model with an interaction term and we carry through the lower... Oh, I just overwrote my poly model. Let's go model interaction right here. These can be called anything. You could call it that for all that matters, but we're just doing an underscore for a space because interaction, there we go, model interaction. This is going to be our interaction model, and you can see it carried through model hierarchy as we were reviewing earlier, because we have the x1, x2 variable, and then we have the here we'll move the plots. We have the x1, x2 variable, and then we have the x1, x2 interaction. So here's x1, here's x2, and x1, x2 interaction. The colon right here stands for weight, which is actually what we would do if we don't want to carry model hierarchy. You can do this. And this now violates model hierarchy because it does not have x1, x2 in the model. So I think Braden is starting to click. I think Braden, you're having these like I'm hoping that you're seeing like, okay, this does not have the weight and GPA variables in the model. It only has weight GPA interaction, which visually is what we're looking at if we were to, I can't erase those. I can white them out. Watch this. Whee! If we were to look at this right here, if I erase them, it's gonna, and that's what we're seeing down here on the bottom. What does the slope mean for the interaction? Oh, no, great questions. Last question. That's what we want. Just keep asking questions. Yeah, the interactions are super new, and we introduced them this week, but we'll go in more depth. The coefficient. So let's carry through model hierarchy. So this coefficient right here, this is in the assignment, and this is the harder thing to interpret. Okay, so let's write something out. The way in which x1 explains y when x2 is larger, x1 has a blanker relationship. So there's a lot of ways. It could be weaker, it could be stronger, it could be more negative. This is probably the hardest part of interactions. I see a lot of just not understanding how to interpret interactions. So the coefficient here, just go from the most basic thing. The coefficient is positive or negative. The coefficient is positive or negative on this. Let me put a cut in this video. This is explaining interactions, because interactions are really tough. Let's go look at that output and explain some interactions. Let's do this. Okay. So here we are with some interaction output, and we've got an interpretation up here we're going to try to use as a structure. And we have a positive coefficient. Excellent work right here. So we see that the interaction between weight and GPA is positive. So let's think about how this impacts weight. So it's not statistically significant. We won't worry about statistical significance in the moment, but you might note it's not statistically significant, which means what we're seeing here could just be by random chance. And truthfully, it's probably due to some multicollinearity that we don't have the significance. But we're going to focus. We're going to focus on what does this interaction mean. With this interaction right here, the way in which weight explains, and I think we're talking about height, the way in which weight explains somebody's height, there it is, the way in which weight explains somebody's height, we see weight right here explaining height, depends, so the way in which weight explains someone's height, y variable, depends on their GPA. When somebody's GPA is water, weight will have a water relationship. When somebody's GPA is higher, weight will have a water relationship. So think about this. We're going to be using this number here as when we have here when GPA. I made a mistake there. When GPA is higher, weight will have a water relationship. What will it have? So here's the original relationship. And as GPA goes up, weight will have a what relationship? So if this is the original, and if this is positive, the relationship will just get water. Don't worry. So just think about, this is the original, and if GPA gets to be bigger numbers, what would this do? And I think drawing this out mathematically might help. Let's write this equation and just think about this, which is something we'll start covering next week. So interactions are all explained in the same light. Well, so it would be stronger. Exactly, it would be stronger. Yes, exactly. And I'll show this. Like, showing it might help too. If we go here to visualize model, we can see this, that when GPA is higher, weight, and let me decrease fonts. When GPA is higher, so let's look right here. For higher GPAs, do you see GPA larger? Weight has a higher coefficient. Do you see how the slope is bigger? When GPA is higher, weight is going to go from its coefficient to a higher coefficient. This is the higher GPA line. Does this make sense with what you just said? Because you saw weight has a positive coefficient, but when GPA is larger, you said it would be stronger. There's going to be a higher coefficient, a more positive coefficient. Does that make sense? The coefficient will go up, but you have to be careful because going up doesn't always mean stronger. You have to look, sometimes it could start out positive and go negative. So let's think about the way it works with the way in which we can talk about multicollinearity next, because that would be a branching. We can talk about that next if you want, definitely, Braden. And then Emily will do your question. Do not worry. Look at this one right here for this output. Let's look at the coefficient of GPA is currently what? Negative. Do you see how the coefficient of GPA starts out negative? It's probably somewhere in here. But as weight goes up, for larger weights, the negative coefficient right here will actually start to become what? Like maybe it starts out about here at the median. It's a negative coefficient to begin. But for higher weights, the coefficient of GPA actually becomes what? For higher weights, the coefficient of GPA actually becomes what? Because the way in which GPA explains someone's height depends on somebody's weight. Is this starting to make sense? Like the way it actually becomes positive, exactly. So what if I said to you, does GPA have a negative or positive coefficient? So look at this especially because you can then answer it. Does GPA have a negative or positive coefficient with height? So you don't want to look at this because that'll trick you. This will trick you. Does GPA have a negative or positive coefficient with height? Does GPA have a negative or positive coefficient with height? And the answer is in here. The answer is not this. I mean, technically, we're talking about the coefficient of GPA, but it's not going to be constant. The coefficient of GPA is not constant because of the what? Technically, the coefficient for the single term, but it's not constant. You would have to say the coefficient of GPA is going to what? Think of a D word. The coefficient of GPA is going to what on what weight is? The coefficient of GPA, actually, because here's different weights, the coefficient of GPA, like if it's positive or negative, would actually depend on what somebody's weight is. For higher weights, think about it, we're adding this on. So it would depend, exactly, it depends. So the coefficient of GPA actually depends. That's what an interaction is doing right here. The coefficient of, because we talk about this right here, where's our thing? The way in which x1 explains y depends on x2. So if I ask you, that probably is a better way of phrasing it. How does GPA explain somebody's, like what relationship does GPA have with somebody's height? Well, that actually depends on somebody's weight. When somebody has a very high weight, the coefficient for GPA is actually positive when somebody has a very low weight. So you could actually do this also right here. When someone has a very low weight, the coefficient for GPA is actually what? See, when weights are small, the coefficient is actually what? Which is what it starts out originally as. Is this making more sense on how to interpret these? I'm going to put one more cut in this video. I'm going to show how to write these out next, and then we're going to hop over to Emily's question. And we can do we'll do that. And so, Emily, we're going to do 2 more topics, and then we'll hop over to central limit theorem on this. Is this making more sense, Braden, right here? Like, the coefficient of somebody's GPA, which is behind me, depends on their weight. The way in which GPA explains height depends on people's weights. Yes, and so this is also important. Let's write out this model. So what I'm going to do right here is I'm going to take this information. We'll leave it on the screen there. I'm going to show you a trick. Here's some magic. I'll see a magic trick. Watch this. There we go. That's LaTeX writing. Yeah, LaTeX. We'll go height equals to this plus this times this plus this times, I guess technically the coefficients come first. Some statistician's going to jump in the channel and say, put your coefficients first. And I'll say, I'm sorry. Because it's B1x1, B2x2. Always, statisticians always jumping into our channel being like, hey, I'm a statistician. You got to do this properly, or you got to put your coefficients first. And I say, it's math. Math doesn't care which order we do it in. So there we go. Let's take a look. There is our model. So we have here that height, or we could put predicted height technically. So predicted height. Increase font. Cool. Yay. There we go. Predicted height is predicted. Oh, it did like a, I didn't know it would do that. LaTeX. Why you do that? So we can't do that. We have to go predicted height like that. Predicted height is equal to 6.2. Oh, let's delete some decimals. We don't want that many decimals. Sure, annotate some decimals. Round. And sure. Okay. Predicted height is equal to 62.06 plus 0.038 weight plus 0.185 GPA plus 0.011 weight times GPA interaction. So what we have right here is the implicit line. This will be on the next assignment, so get ready to write out some equations on the next assignment. But what if I told you, solve this line right here, solve this when people have a weight of, let's say, 100. What would you do for this? So Braden, this is a really good skill for the next assignment. What would you do here if we said solve this for when people have a weight of 100? Just don't think too hard. Be like, just go back to algebra and be like, what if I said solve this for when people have a weight of 100? Solve the implicit line for when people have a weight of 100. We could also solve the implicit line for when people have a GPA of 4. So just like, wait, you want me to solve this when people have a weight of 100? So what would you do? Start typing out the answer. I'm going to start working on it and think about what we would do if we just said solve this for when people have a weight of 100, which is when we solve an implicit line. Next assignment. So if we were to solve this for when people have a weight of 100, we're just going to take it and go right here and go 100, 100, and we have this right here. So we're just plugging 100. All I did, just so people can see, is I went to where, okay, good, it's doing below. That's awesome. All I did was just take wherever weight was, and I just plugged in 100 to solve the implicit line. So when we say solve the implicit line for this, you just take the equation, just fill in the equation as much as possible with weight 100, assume we don't know GPA. Boom! That's when we solve an implicit line. So do you remember those lines we saw just a moment ago over here? These are implicit lines solved for like when weight is equal to a certain amount. This is solving the equation. We're just drawing some of these lines right here because we're turning it into just a one variable XY relationship by solving for certain amounts. So these lines right here are drawn via the same way as us taking and solving the equation right here and putting in certain values. So all we're going to do is times this by 100. So if we times this by 100, we'd get the following. And let me delete off the 100. And then we go right here. This times 100 is going to turn into this. And now what do you think we're going to do? All we're going to do now is combine like terms. So all we do now is just go here and put the 3.8 into this. And so that just combined into that. And now we put the 1.1 into this. And so that'd be 2.9. Oh, no, it was negative, right? It was negative, right? It's negative. Oh, no, no, no. This was negative. The interaction was negative, right? No, GPA is negative. GPA is negative. That's the issue. I knew there was a negative to positive. I am very sorry. This should be negative. That's an error. I was like, something didn't work with the graphics. I was like, the graphics didn't show that. They showed a change. This is, we can definitely do some of that, Ryan. I'm trying to remember, which one do you want to go over, Ryan? This is us talking about probably next assignment. We started off talking about interactions on the last part of task 2. So check out the start of the video, interactions on test 2. And feel free to ask any questions. This is talking about how to write implicit lines, which will be on the next assignment. So we did interactions to start this, and we're just going to put these together mathematically. We could double check our work here. So we could go negative this plus this, and we should get, we're just combining these terms. And there we go. We could have figured that out in our heads. We could have done that. And that is the answer, Braden. This is the answer to what is the implicit line for when somebody's weight. Awesome. Glad to hear that. Awesome job, Ryan. This is the implicit line, Braden. And if you notice, it would just create one of these relationships like we see over here to where we see the line like an XY relationship between a variable. So we can solve implicit lines by plugging in the numbers. All we did was plug in somebody's weight, and we can then solve out the equations for an implicit line. So just knowing this idea of plugging in the numbers and then reducing the equation is going to be important for the next assignment to solve the implicit line. Like solve the implicit line when someone has a weight of 100, solve the implicit line when someone has a weight of 200, and then you'll see that you're creating these lines that are being used. Yeah, anytime. Yeah. Anytime. Just swing by and we put it in the video. The only last thing to mention, which you brought up, which I'm more than happy to mention, is the variance inflation factor, which we should have it in the interaction model. And yeah, so this is why we don't have significance. I mean, it has to be, because when you have interactions, the interaction right here is built off of these two variables. So variance inflation is the shared, put another cut. I remember to put all these cuts in my videos so I can come back. So for people to watch them later review. So here we go. We'll go back there. So variance inflation with our interaction model is, once again, multicollinearity, which is variance inflation. Multicollinearity is the shared variation between multiple variables. Like you think about collinearity, like sharing, like the linear relate, or sharing, like correlation, collinearity, kind of similar terms right there. Multicollinearity is if we have multiple x's sharing sources of variation. That's what multicollinearity means. A way we measure this is with variance inflation factor. You do not want high variance inflation factor, but it does not invalidate the model. I can't state that clearly enough. What would variance inflation factor do? It's just going to add more uncertainty. And we can see this mathematically over here, because when you think of variance inflation factor, there's what it stands for, but it's actually standard error squared inflation factor, because standard error is squared is variance. So when you think about what we're doing right here, if we have here's a perfectly fine test question about how much more uncertainty do we have in the coefficient of GPA? About 4.8, or probably about 4.8. Why am I saying 4.8? I'm taking this number and I'm just square rooting it. And that's about how much more uncertainty we have. I feel like regression with regression to have two of the x variables also to each other. Yeah, exactly. You don't want the x variables explaining each other. That's exactly it. You don't want your x's explaining your x's. If a model actually has perfectly collinear x's, it can't use them. And we can show this very quickly. I'll show you a model, like, let me go to survey 10, and let me take height, and we're going to make a model from height from weight. And we're going to put here survey 10, and we're going to put here height 2. So would you agree with me that height 2 is just height? So let's make a model now explaining weight from height. Well, we have height 2 right there. So height plus height 2. So would you agree it's the exact same variable, which means all the variation is overlapping between them. They're the same variable. So since they're the same variable, let's see what happens when we try to make this model. It will make it, but when you go to look at the coefficients for height 2 do not exist. And we should get, it should be interesting, because the variance inflation factor, it's saying there's alias terms. It can't do it because there would actually be infinite variance inflation. The variance inflation factor here would be infinity, and sorry, I'd sneeze. So the variance inflation factor would actually be infinity. We could fix this. I could make it almost not infinity. Let's make it almost not infinity. Let's overwrite and put that in. There we go. Now it can do it. And let's look at the VIF. Wow, I must have really made a big change to that. I'm shocked. Oh, we put a height of 100. There we go. Much better. So that really changed the variable. But I wonder what they were originally. Let me go look at their original value. The original value of that individual was 69 inches. Okay. So if I were to put it very close to that, it would go even higher because the sources of variation are going to be even closer. Well, it's not. If we put it back to 69, now we can't estimate them. What? What have I done to this data set? Are they not? What have I done to this data set, everybody? 62. Okay, there we go. I was like, that did not make sense theoretically. Because now it doesn't estimate it. Yeah. I was like, it's not going towards it. There we go. That's wild changing 1 point. Well, yeah, exactly. And you notice right here, the VIFs, as I go towards 62, which is what the number is, the VIFs are approaching what? As I go towards 62, the VIFs, like, look at this. This is ridiculous VIFs. As I go towards 62, the VIFs start to approach what? And now actually it won't even do it. As I go towards 62, the VIFs start to approach what? Because now the variables are almost overlapping completely. Like it's almost the exact same information. So the VIFs approach what? Which we can show mathematically. Mathematically, the equation is doing this. This is what's happening mathematically here. And, well, it's going to put in scientific notation, but it's doing this. Really? I don't want scientific notation. It's approaching infinity, exactly, because this is the r squared of the shared variation between the x's. When we calculate VIF, we're looking at the formula 1 over 1 minus r squared sub I, and the r squared sub I is the r squared of the shared variation between the x's. So we don't want a high r squared sub I. That's a perfectly great test question, like, a high r squared sub I is a good thing. No. High r squared sub I would lead to what? Multicollinearity. This is the formula for variance inflation factor here. And variance inflation factor is how we measure the shared variation between the x's. This r squared sub I is a model where we have an x variable being explained by your x's. So you do not want this. So I guess it's x sub I and then all your other x's. But you're looking here at your x variables being explained by your x's. This is a very bad thing because, Braden, great question. We're going to do Emily's here. What does this mean? Your x's, if they overlap, are not bringing what with them? If your x's overlap, they are not bringing what to the model? That's a key thing for multiple regression. You're like, wait, but I thought we want things to explain each other. But if your x's explain each other, then they're not bringing this with them. They'd be bringing redundant this. The information they bring is redundant. It would not be this. New information, exactly. We want new and unique information where each x does something unique in the model, but it's not that height 2 is a bad variable. Height 2 is a bad variable in this model, hence it's not significant because, now they're both not significant. Ooh, what's going on? Neither one is a bad variable, though. They're both fine variables. It's just that they overlap in what they do. You see, that's significant by itself. That's significant by itself. But if you include both of them, then they're both bringing the same sources of variation, and you get just, this is a ridiculous model. This model right here, nothing is significant. You want to talk about paradox? Is this model statistically significant? Is this multiple regression model statistically significant? Is the multiple regression model statistically significant? Is the weird paradox of multicollinearity? Is the multiple regression model statistically significant? Weird, multiple regression is so cool. This multiple regression model is not statistic. I mean, it is. Oh my God, my brain broke. It is very, very, you got it right, Braden. You are correct. Sorry, you're like, what? No. It is very, 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 very statistically significant, but none of the variables. We don't care about the intercept. Intercept is just when x's are equal to 0. No one cares about that. The coefficients in the model, the x variables are not statistically significant, but the model itself is statistically significant. And this is definitely ridiculously due to the variance inflation factor. We created a ridiculous model. So I hope that helps out, Braden. Thank you so much for asking all those questions right there. That's a lot of really great questions. Let's talk, Emily, if you're still here, about some central limit theorem. So the central limit theorem, especially how we're applying it. And Braden, ask more questions if you got them. I'll definitely do them here. Thank you so much, Braden. I was like, I guess I'll just do some random questions to start, but then we got people. Okay. Central limit theorem, if we meet, let's put this, meet all of our conditions. So if we meet all of our conditions, what will be true? So if we meet every one of our conditions, what will be true? Awesome. Great job, Braden. You're welcome. Appreciate it. Anytime. Swing by. So if we meet all of our conditions, what will be true? Well, let's first look at those conditions. I've got it up over here still. No, I don't. Let me go grab those conditions and put it in the video right here. Step 201. Here we go. Let's go grab the conditions. And the central limit theorem explicitly applies to the normal curve. So what we're talking about right here is the normal curve, and we need to meet the conditions. Explicitly, today we're talking about the random, which is what we always have, the 10%, and then we're going to be talking about the large enough n for chapter 13 right here, or the new stuff for test 3. So when we meet these conditions, when we have randomly sampled data, less than 10% of the population is sampled, and then also depending on what kind of data we're dealing with, if the data is categorical, so we need to use success failure. That's not green. I'm going to reinstall Word. I hate that you can't have more than a few pens. I used to have so many pens. And quantitative. The bottom one down here is chi-squared. Is test 3 our final? Yep. Test 3 is the final. You bet. Great question. Thank you so much. And this is chi-squared. So we have quantitative data, categorical data, and chi-squared. So when we meet all three conditions, what does this tell us about the distribution we'll be dealing with? What will be true about the distribution? Two things will be true if the central limit theorem works. Like if we meet the conditions, the most important one that comes into play a lot is one, it will be more this. Which it's two things it'll be. The one that we really care about is normal. Second, it'll also be tighter. It will be tighter. So it'll be more normal and it'll be tighter. So let's kind of see this in action right here. Let's see how this works. So let's go over here. Go to central limit theorem applet. And oh, someone's got a different applet? That's not our applet. Where is it? Is this it? Aha, found it. People have made more applets. So we need to meet the conditions. So let's see if we meet the condition with the following. The nearly normal condition, and we've got some notes from class today, so let's show those. Here are the rules for the nearly normal condition. It's summarized here. I'm going to vanish. It says right here, 25 is usually large enough for most populations, 100 for very skewed. I couldn't find that yesterday, even though it was at the bottom of the slide. My brain just blanked. But I like to say it this way. Here's my summary. Whatever your lecture screen. Here's my summary of the condition and the way to think about the nearly normal or large enough n condition. And this is for quantitative data. Make sure you know this is for quantitative. This is for quantitative data. This is for quantitative. So when we do the nearly normal large enough n condition, the first step is to ask what the shape of the distribution is. So Emily, big question right here. What is the shape of this original distribution? So how does it look? How does this original distribution look up here? That's the first question you ask when doing the central limit theorem? What is the shape of your distribution? And you can investigate this with a histogram, a normal probability plot. So histogram, normal probability plot, or goodness of fit test. Not box plots. Normal, you are right. It is normal. It is normal. So since this is normal, let me ask you, is 5 going to be large enough that the new distribution down here will be more normal enough? That's what we mean by nearly normal. When I do this and we meet these conditions, if it's normal, so we have to ask, what is the number? Number's 1. And then do we meet that with how much we are sampling? Is this sample size of 5 going to be large enough that when I run this, the one down here will be nearly normal? So will this sample size of 5 be large enough that samples of 5, like if I take samples of 5 and then I compute the mean for this, I take a sample of 5 and then I compute the mean. And if I do this repeatedly, I keep doing it, will this new distribution actually be normal or not normal? And so remember, we said it was normal to begin with. Then we say the number for normal is 1, and do we have at least that? So the answer to do we have at least that will be, do we meet the condition? Do we have at least 1 right here? Do we have at least 1 right here? It's gonna be nearly normal, and boom, you got it. Look at that. That is, we met the central limit theorem. What else do you notice about this? We met the condition, and it is looking definitely normal. And what else do you notice about that distribution when you take a look at it on the screen right there? That distribution looks water to the other one. We met the condition, and it's going to be more normal, and it also looks what compared to it? Like when you look at the top one versus the bottom one there, we wouldn't do that. When you look at the top distribution versus the bottom distribution, it does look more normal, and it also looks what? And that's the two things the central limit theorem is stating. Looks tighter, exactly. So it meets those two things right here. Okay, let's try another example here, but similar, where we have a very skewed distribution. Now, for this, yes, David M. Lane. For this once it kicks in right there, we can do the David M. Lane for this distribution right here. And good to see you, Catherine. So let's throw out some points too. Thank you, everyone, for swinging by. When we meet, let me ask you this first. Step 1, what is the shape of that distribution? Over there. What's the shape of that distribution? Hey, if you have any questions, let me know. Skewed right to the high, left to the low, whatever way the tail goes. Still skewed though. So it is right skewed because the tail goes to the high side. Right to the high, left to the low, whatever way the tail goes. Always think about drawing the monster man. So monster woman, monster person. So do not worry. We just practice. We say, here's our monster person and there's the tail. So whatever way the tail of the monster goes, right to the high, left to the low. And what do we mean to the high? It's pulled out to the higher numbers, right to the high, left to the low, whatever way that tail goes. And there we go. So when I run this right here, to meet the central limit theorem, I need to have a sample size of at least what? So we just said it's skewed. And it's maybe not, it's just skewed. We'll just say it's just skewed. So we saw that by looking at the histogram. We could have also, there's other ways, normal probability plot, goodness of fit. Those are other ways to investigate the shape. So since it's skewed, our sample size needs to be a what? What should our sample size be? Since it's skewed, our sample size should be what? And then go down to here. 25. Great job, Emily. Yep. So, I'm gonna draw my pen. Since it's skewed, the sample size needs to be 25. Is our sample size that we're doing for this problem at least 25? Is our sample size for this problem down here at least 25? Does this meet it? Yes or no? Do we have at least 25 that we're doing for the sample sizes? We'll watch right here, watch it happen. There's a mean of sample size 2. There's a mean of sample size 2. And it's just going to keep doing this. Every blue dot is the mean of 2 observations. You're right. So this distribution will look normal or not. You can just say yes or no. So will it look normal? When I keep doing this and I make a distribution, will this look normal? Because you said this is not enough to meet the nearly normal. So if I keep doing this, you think you said no to it. Look at that. It still looks skewed. But if n were to get larger, what happens as n gets larger? What do you notice each distribution, which I'm like fast forwarding in time through? As n gets larger, it actually gets wetter and wetter. So we'll start at the small n right here. And you notice there's an n of 2, there's an n of 5, there's an n of 10. As we go up in sample size, like 25 observations averaged together, and so one blue dot is 25 averaged together, and we do this process a whole bunch of times, and the distribution starts to look two things. It'll look normal and tighter. And at this point, just looking at it visually, do you think the sample size here is large enough? Just looking at that visually, does that look, it kind of looks something, right? I mean, not perfectly this. Exactly, it got tighter and more normal. And at this point, you might say, you know, that kind of looks this to me. That kind of looks what? And that's the name of the condition. That kind of looks this. It kind of looks nearly normal. And why does it look nearly normal? Because we had a large enough n. Does that help draw it together, Emily, maybe a little bit? Like, it starts to look nearly normal because n was large enough. So we're seeing it looks nearly normal now because n was large enough. When n is not large enough, it does not look nearly normal. Yeah, that's good. Yeah, no, it's just like it's like a brick building thing. We got to get there. Like, no, great job, Emily. Great job. More questions if you have them. We're out of questions right now. You're welcome, Emily. Thank you for coming by and asking about it. You know, I think it's going to help people like walking through the central limit theorem and what it means to have large enough nearly normal. You know, I don't know. I like every semester I teach these topics. I think, how can I teach it better? I'm one of those crazy people who's like, I got to improve, got to like make everything better. It's like, I don't know. Once I realized like when you draw together the names of the conditions for, I think that's what helps. Like, we want the shape of this to be nearly normal, and it will happen when n is large enough. Oh, also, where's the survey? Yes, let's. I'll send out an email about that. I'm too afraid to put in a public video lest people start like trolling our survey. Send me an email, Emily, or I'll be sending it out to the class probably here later. But the results of it. Results. Here's aggregate results. This is. Oh, you're welcome, Catherine. Thank you so much. Like, I appreciate. I like analyzing data, and I like, helping out. That awesome. Oh, Emily, email me here. Emily, I'm going to remove that since, wait. I'm just going to, wait. Since it's on a public video. So like, these are all public, nothing like, don't worry. It's YouTube. But I always like, since we're on public videos, I don't like post links. Sometimes that makes sense, Emily. If you want to remove the message just in case, because technically anyone who watches the video, not like, it's just like, it's like commenting on Instagram or stuff like that. Does that make sense? Like comments anywhere on the internet or yeah. So I just always want students to understand that like these are public videos, but then during class I put those up as unlisted videos. And unless people were to like, it'd be the same thing as someone like going into a Zoom class. Yeah, Emily. Yeah, don't worry. I just always want to, I don't know. I care about my students. I don't want any like, I don't know. It's just, the internet's such a weird place. It's like so good and then just so like, why you got to be that way, internet? We've seen some really good advice right here. Watching the Kahoots, people who watch the Kahoots. After this topic, could you go into more depth on the interaction? And yeah, which one, Ryan, which one were you wondering about? What would you like to know about, Ryan? Explain what you want to know about interactions, and let's do that next. Here's my advice for students that we have for 201 so far, and I'm going to send this out more. But look at the statistical significance here. I mean, I know it's just barely, but we see that watching the Kahoots live, people who are watching the Kahoots live are doing better. We saw some big advice, though, coming up. You know what I'm going to do? I've been meaning to do this, and we haven't done this yet. Decision tree time. Let's find the path of the A and the B student. We can't. No. The best predictor right now is what did you expect? Which is interesting. If you expect to do well, you do well. But you don't really control what you expect. So I'm going to remove that because it's a great variable. It's the best variable, but I'm going to remove it. Canvas content. Canvas content is the number one deciding factor so far. And look at the grade differences between people who have A's and don't have A's. There's a 15-point average difference on the test. So if I keep telling everyone, do the Canvas content. See, I did the live Kahoots and watched exam 2 Kahoots for the former years, but I feel like the questions on the test were a bit harder than the ones on the Kahoots. Yeah, And some of the Kahoots are very similar, and some of them it's hard. Like, I base it off some of the questions, and then sometimes I take direct questions. Like, sometimes there's a direct question or two on the Kahoot, and then sometimes the questions are, did you do all right, Emily? You can put your grade in here if you want. But I think if somebody made in the high 70s, they should feel happy. And you can still make an A in the class, especially with the curve, if you made in the high 70s. If you made in the 80s, awesome. If you made in the 90s, great job. I'm sure I'd even make some errors on this test. Because there was one we were debating back and forth as instructors, and I was like, yeah, I guess it should be read that way. Because there was one I was like, well, and everyone was like, we were all talking back and forth, and I was like, okay, I see the way it should be read. Maybe I'm just reading it wrong. So I did better than yeah, that's fine. That's fine. And with and that's not with the 7, right? Did you hear about that? Oh, if you're in today's class, you would have heard it. There's a 7-point curve on the test. So interaction explained, you bet. Let's go back and do that. I think at the model hierarchy, but not the interaction. You got it. We'll do that here in Ryan in 2 seconds. Thank you so much, Ryan, for hanging out. Yeah, 7-point curve, right? Woo! I was gonna hit the randomness. Why not? I'll be sending out that announcement in just a little bit. That was getting decided upon this morning. So one class has already heard about it. I know, right? Really great news. I was basically trying to tell everyone, hey, we're working on this. Look at this. People who did chapter 13, the highest grades right here, these 55 individuals are people who are doing the Canvas content. Yep, Emily. How do you feel a lot better about that now? I hope. Like, that's so then the people with the highest grades, they never watch Kahoots. That's interesting. Maybe I should just let the tree do its own thing and not tell the tree what to do. That's so weird that SI always has that relationship. We saw that last time too. I do not understand why that happens with SI. And then finally, when you started studying comes into play, and within 24 hours, the people who started studying, but then they're actually doing better. It's really what you do beforehand that matters. So looking at this tree, the people who are doing the best are people, the people who did the best on this exam did the following. They have A's on Canvas content. They hadn't completed chapter 13. That's odd. That's a small group right there. And then they don't go to SI, and then they started studying within 24 hours. It's only 8 individuals. These 55 over here, I'm going to divide them up further. I want to see the highest group up here. So they have let's divide this. Okay. So, yeah. Oh, this makes sense. Okay. So these 7 people over here on this far side have a 91 average. Can I divide them up? Nope, too small. Didn't think so. Okay, so the pathway right here, these people who made the highest grades have an A on Canvas content. They did chapter 13 at some point. They either watch live or never the Kahoots. So like these people watch the recorded Kahoots. These people watch live or never. I guess if they're watching live, they're interacting, and maybe, I don't know why that. Then how often do you chat during class? They often chat during class. What degree of attention do you have while watching class? They're very attentive. So these are very attentive, talkative people who may or may not be watching the Kahoots. They did chapter 13 and they do their Canvas content. A lot of this goes in line with come to class, do the work, be attentive. It doesn't mean if you do those things, you'll make an A. Doesn't mean if you do those things, you'll make an A. But we see over here, these 7 people had a 91 average. There is a good bit of variation in them, though, with a variation of that right there. I don't think candidates shows them, does it? Yeah, I never. Those candidate split items. But yeah, good stuff right here. Very interesting, and I really like. I don't know. We'll get more data on this, and we'll take a look. Let's hop back in here, Ryan. And take a look. Or yes, Ryan. Okay, good. Let's do this. Okay, Ryan, you were wondering about interaction explained based on the 2 models for task 1. I think I'm all hierarchy part, but not the interaction. Cool, let's do interaction. Here we go. Where did I put the interaction term? Interaction term right here. Okay, so when we talk about interactions, this is what an interaction looks like right here. So here, Ryan, if you're ready, here, don't worry if you get this question wrong. I'm going to throw some 50 points out here for positivity. Do not worry if you get this wrong. I want to ask you, what kind of relationship in this model does GPA have with height? I want to ask you, what kind of relationship does GPA have with height? What kind of relationship does GPA have with height? What kind of relationship does GPA have with height? Let me put a cut in the video. I'm back. We're going to talk about interactions. Let's do this. How to talk about and explain interactions. The question is, what kind of relationship does GPA have with height? So this is an interaction model right here. What kind of relationship does GPA have with height? So what kind of relationship does GPA have with height? How does GPA explain height? In what way does GPA explain height? And if you look, you see this right here. You also see this. You also see this. I'm not sure is actually the right answer because we'd need more information. We'd need information on what to know the relationship GPA has. So Ryan, that's another 50 points. The answer is I'm not sure. That is really the answer is I'm not really sure at this point. And why? Because of the interaction term, the way in which, let's look at our notes right here, the way in which GPA explains height depends on somebody's weight. When somebody's weight is larger, then GPA will actually have a positive coefficient. It's actually going to go from a negative to a positive coefficient from smaller to larger weights. So let's look at this again right here. We have the answer right here, which we have to plug in the variables for, and also we have to kind of look at the graphic and think about it. And we can also look at this mathematically here in a moment. But the way in which we have x1, which is this, GPA explains y, which is somebody's height, depends on x2, and here's where we're doing the depends, like this will change the relationship of GPA with height, so it depends on the weight coefficient, which is x2. When weight is higher, which we can pick, and look, you're going from smaller to higher, then GPA, which is x1, is going to have a stronger, or we could say more positive relationship. It's going to go from a negative to positive coefficient. So you can also see this here if we look at the summary output. So in the summary output, we actually get the numeric values that GPA starts out as a negative coefficient. And if we increase, here's the interaction, it would become more positive. So this right here is showing us it starts out as a negative coefficient. Technically, we have right here when weights are equal to 0, then the GPA coefficient would be equal to this. But as weights start to go up, it eventually becomes a positive coefficient. GPA becomes a positive coefficient. Is this starting to make sense here, Ryan? Like the way in which GPA explains height, because height is the y variable, the way in which GPA explains height depends on the value of weight. And what we're doing here is we're plugging in values of weight. We have this over here on the other assignment where we can plug in the values. Here's the equation written out. So just take a moment right here on this screen. I'm going to make it really big so we can see it really well. Awesome. That's what I love hearing, Ryan. Thank you so much. And if it doesn't make sense, also tell me that too. But I love when things make sense. If you take a look, this is the equation. So what I've done right here is I've just taken all the coefficients. So just realize we just taken right here, we have the intercept. Intercept is up here. Good, that's an equals. We have weight right here times its coefficient. We have GPA, which is negative, times its coefficient. We have the interaction term, because this stands for the interaction term, times its coefficient right here. So what we can do then is we can just plug in a value like 100, and then we would just solve through. So all we're going to do is just solve this out. And look what would get added together, 62.38, because when you times it, you get 62.38. Well, that would be 65 right here, 0.38, when you add together these two like terms. How about the other like terms, though? This right here, 100 times this, is 1.1. Negative 1.85, adding to 1.1 is going to be this right here, when we add together these two like terms after we reduce. Just so you can see what happens when we reduce this, 100 times this is just going to move around the decimals a little bit here. And so that moves the decimals, and then we're just subtracting, and that's how we're obtaining this number over here. Same thing goes for this. When we times by 100, we're just moving decimals. And this is solving the implicit, and then we just would take this, 62.06 plus 3.8. There's that term. And then we'd also take over here negative 1.85 plus 1.1, and we get the following term right there. This is solving the implicit equation, which is not on this assignment, when we have certain values of x that we are using. You could solve this for anything. And what would happen if we put in somebody's weight of, like, let's say 300? If we put in a weight of 300, think about this. This right here is going to turn to a more positive number. Hey, Lurka! It's going to turn to a more positive number, and we're eventually going to see this positive coefficient at the end that it becomes positive. Is there any chance for regetting exam 2 like there was for exam 1? Possibly go over questions. Yeah. I can mention the Lady Vol shooter one. And then that equation will be exactly. That's what we're getting right here. These are the lines because we're solving individual lines. And I'll send out an announcement, Lurka. I've got a good announcement with the first class already heard. This equation right here is the equation of one of these lines. So these are called implicit lines because we solve for certain values of weight, and then we get these lines. Ryan, you're getting it exactly by hearing that. So yeah, I'll do a variation on the Lady Vols one here in a second. Excellent question, Lurk, X. So I was trying to pronounce it correctly right there. But does that make sense? Each one of these lines is solved out for different values of people's weights. So you can see this is a small value of weight, the median value of weight, and the large. And I think this is 10th percentile, 50th. That's median, so it's 50th. And this is the 90th percentile of weights. So let me reappear. Wow, I'm back. So let's do a Lady Vol type question. So for the Lady Vol type question, the Lady Vols are, what is it? How does it work? It was like no overtime, right? I'm trying to think. Let me put a cut. I'm trying to add cuts in the video. They help me out so much later when I'm reviewing the video later tonight. You're welcome. I'll see you in class here in a little bit. So excellent work, Ryan. Great job. Let's go check out this question. Here we'll go. What is it? The Lady Vols, they got 2 shots, right? And so is it if they make... Okay, so they are down by 1. The Lady Vols are down by 1. 2 shots, they're down by 1 point. What's the probability of overtime? Exactly. So, well, was it the probability of overtime? I think it was not overtime, right? So, oh no, I think it is the probability of overtime, right? Yep. And I'll explain why. The Lady Vols are down by 1. They have 2 free throws. I think you got it correct. The probability of each is independent. They have a 20% or whatever, 20%. Oh, we can't do that to them. 80% probability of making a free throw. What is the probability of overtime? Okay. So let's think about this scenario right here and graph it out. We've got a few things that could happen. There's 4 possible things that could happen. Tell me the one that I'm missing that we hope would not happen. So I'm going to draw this out visually right here. And here's what could happen. I'm drawing out the 4 possibilities. I'm going to leave 1 off. Think about the 4 things that could occur. And I'm going to leave off 1 of the possibilities. So think about the 4 things that could occur right here. What are the 4 things that could occur? So you think about the 4 things that could occur right here. So what are the 4 things that could occur? Miss both, exactly. When do they go to overtime? Pen is haunted. When do they go to overtime? Here. Would you agree these are instances that they go to overtime? There's quite a few ways to solve this, actually. So there's 2 ways to solve this. So for them to go to overtime, they would have to either... So you could say this. They either miss the first, make the second, or make the first, miss this one here. So you could just take these and add these. So mathematically, this would equal up to 0.2 times 0.8 plus 0.8 plus times 0.2, because we have what's the probability that they miss the first and make the second, or they my brain's breaking, make the first and miss the second. And there's another way of doing it though, because we could also say these are the things we're not interested in. So going to overtime would be everything but, here's everything 1, everything but they miss both shots, or, so we'll put this inside of a big parentheses right here, or they make both shots. So everything but they miss or make both shots. And so this would give us the yellow region also, because we have the set of all events. And so we should get right here, we can solve this by going here and doing, it should be 32%. So there's that. And then we're just adding another version of it. There's 32%. And then right here, we get 0.02 times 0.02. And let me see. Oh, I did 0.02. I was like, something went wrong there. There we go. There's 4%. And here's 0.08 times this. There's that, plus 4%. And then we do 1 minus, and we get that right there. Does that make sense there on the region we're looking for? We're looking for the probability that basically they make one or the other shot, which can also be assigned as the probability that they didn't make or miss both shots. So I hate probably, do you have like a method to solve these? Yeah, the hardest thing, X, is I always try to draw them out, and then I try to make sure that yeah. And this is a tough one. I think hopefully with the 2 solves it helps, because what you always want to do with probability is you always want to make a drawing for it. Like that helps me a lot. Ever since I used to trip over my words with these and be like everything but the blah 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 blah. But when you see this right here, this is making both shots. Like this right here is making. This right here is missing both shots, and everything but making or missing or making both shots is going to be this region right here, which is they make at least one. Or not make at least one, excuse me, because that would be 1 minus miss both. So see, it's really easy to say it incorrectly. But drawing this out hopefully shows this is the region we're looking for, which can also be assigned as this first one, which would be here, plus this second one, which would be here. So I think the drawings can really help. Like that's what I always try to do, is I always try to draw it out. The more you can draw it out, and I think that helps explain it. They're pretty tough. It's practice. Just try to do as many practice problems as you can. And then I think that's what we often forget, because it amazes me too a lot of times that you have to do like tons of problems. I heard some good advice from a math teacher. Someone was like, well, how do I get good at math problems? He's like, don't try to understand one math problem. Try to solve 50 math problems. So by the time you solve like 50 of them, because he was talking about doing like integrals and stuff, when you solve a whole bunch of them, your brain just starts to create these habits and create these like, okay, I've seen this, I do this. Yeah, no worries. And the good part is we're not doing probability anymore, but probability mathematics is a very important field, like dealing with fractions and percents and what is the likelihood of an event. It's very, very useful. It's we only do it a little bit here, but I mean it's a major part of mathematics is probabilities. So yeah. Awesome stuff, Lurker. Great question. What other questions do people have? Feel free to ask. I've got like a interview thing coming up here soon. Not an interview, but like and they said, can I talk to you about this? And Publicis Pro. I was like, okay, sure, whatever. It was my fault for starting late. Yeah, it's so weird. I just can fly by Calc 1, Calc 2, Calc 3 A's. But that's the thing about mathematics, X, is it's totally different stuff. We're going to go to space and listen to some music. No, it's very, very different fields. Like trigonometry, I cannot do trigonometry. I should have practiced trigonometry more. Like you can stump me easily, be like, "Hey, Brian, here's a dodecahedron." It's just a fun word to say, and I'll be like, "I have no idea how to handle it." I'd be like, "What's the surface area on it?" And I'll be like, "I cannot calculate surface area. I don't know how." You're like, "It's just an equation." I'll be like, "I don't understand. I don't understand trigonometry. Really bad at it." And I'm okay at calculus. Linear algebra I always liked, but my linear algebra skills have gone. My calculus skills are probably gone too. I retook differential equations a little while ago. Wasn't the best of experiences. I was really bad at trig, yeah. But since calculus uses so much of it, yeah, exactly, like unit circle and all that stuff. Yeah, calculus uses a whole ton of like, because you got sine, cosine, arctan, all that good stuff right there. Like calculus uses a ton of trig functions. So like it like forces you to like practice up and know, what was it? cosine goes down. Wait, no, sine up, cosine. Cosine starts like that. So on the unit circle, cosine 0 is 1, right? I honestly just use tricks. Exactly, unit circle stuff. I use tricks too. Sine up. Sine starts at 0. I always remember sine up, co down. So like cosine goes down. I made that up a long time ago. I can't believe I still remember that. Sine up, co down. Maybe someone told me that. I don't know. Have you ever heard that? Like sine starts at 0 and goes up. Like sine up, co down. So cosine has the hump there at the start and then goes down. And I've always been just trying to make up little things. I think that's what helps me as a teacher, is I as a student was always trying to make up my own mnemonics and stuff to like memorize these things. And then the more you do it, you actually, sometimes you forget your own mnemonics because you'll just do it so much. Like I don't have to think about p-values and be like, when the p is low, reject the null. When the p is high, just let it fly. Sine is y, cosine is x, so it's a radian 0. Yeah, and so it is the unit circle, right? It's the value of, see, now you got to be like sine e, cos x. Like, I don't know, like, I'm trying to think of ways right now to remember, like, sine is y and cosine is x, because there's no reason behind any of that. And that's actually kind of why I like statistics, too. Like, what does sine actually mean, and what does cosine actually mean? Like, why is it called sine? Why is it called cosine? Does that make sense? Like, the p-value is the probability of our results or results from our stream having by random chance variation given that the null is true, and because we reject when it's below 0.05 because they were saying it's unlikely due to random chance, which is what a p-value is. I notice that all the time, like the process so well. Yeah, exactly. Why is it again? Why is it called sine? Like that, like I wish I could restart school from the very beginning and just ask these questions to my teachers, and they might not know the answers. And a good teacher would say, I'll go look into it. A really bad teacher would make up an answer. But if someone asked me, like, why is it called sine? I'd be like, I don't know. I don't know why it's called sine. It's just what it is. But if someone says, well, why is a p-value? Like, what do you mean by p-value? I'd be like, it's a probability. Like, what are we measuring? Well, we're starting out with an assumption and looking at the probability of our observed results, or a result more extreme, hence we shade beyond the result. So, yeah, Kayla, help us out. Why is it called sine? Why is it called cosine? Why? Kayla, thank you so much. Swinging by here. Help us out. Save us. X is talking about some trig and all that stuff. So we're talking about unit circle. I always go back to algebra because I forget some of the factoring stuff. Oh, yeah, factoring stuff. I'm going to mispronounce his name, but this Carnegie Mellon professor, shout outs to him. I'm on my YouTube channel, and I'm subscribed to him here. I have totally different subscriptions on my Mewtwo channel. Here he is, Po Shin Lao, I think, and very sorry if I mispronounced your name, Dr. Lao. But amazing educator, has a really cool YouTube channel. Let's go check out his YouTube channel right here and talk some mathematics. Maybe Kayla has the answer for us on why is it sine and cosine. So let's hop to the main screen. I was thinking about inviting him to this channel. Really cool guy right here. But I have not watched this video. I have not previewed it. But brilliant man. It's all middle school education thing. But he teaches at Carnegie Mellon. He does like math challenge stuff. And so you can see, here we get his green screen ourselves into his video. So we just put ourselves in here. Come from Sanskrit? Oh, what is that? What does that mean? He's got, look at his handwriting, much better than mine. Oh, he's talking about probabilities. But yeah, he coaches like math Olympiad teams and stuff like that. So watch our video get like, but no, shout outs to him. I saw him on Red Pen, Black Pen, I think it is. And I was able to ask questions. And the guy was like, the guy who runs Red Pen, Black Pen was like, Stat 201 UTK. I do not know what school that is. And I was like, no, you don't know who we are. Are independent. Wait, two real numbers A and B are independent and are randomly selected between 0 and 10 inclusive. The numbers satisfy the inequality of gosh. Now we're getting into some algebra. What is the probability that... Oh my gosh. Yeah, Red Pen Black Pen's awesome. That dude is crazy. Yeah, check it out. We're in his stream. So if you go look at one of his... It's when he interviewed Dr. Lowe right here. I actually got a question in and he was like, Stat 201. Yeah, UTK. And I was like, oh, he mentioned our channel. That's awesome right there. They were also used in Latin, if I remember correctly. Sine is Latin for bay. Did not know that. Sinus. Sinus is Latin for bay. So I guess it goes back to like the early beginnings, like when people were first... So why did they do that? Why? organic chemistry tutor, Patrick J&T, Nancy PL to learn all my math. I used to watch him. Professor Leonard's great too. I used to watch him doing wild integrals in Calc 2. Yeah, Red Pen, Black Pen. That dude's awesome. And it's really, I don't know. I want to always encourage more. So I like the way he's doing it. He's basically doing what we're doing. He's doing the same thing we're doing, basically. Same setup, probably. Green screening himself. We're going to cut. Look at it's awesome. You're doing a great job there. You're way smarter than me. Doesn't matter if you're smarter than me, but you know all this mathematics stuff right here. That's awesome. Trig is just, whoo, trigonometry. Actually, stream on Twitch doing some Calc 3 stuff, testing out my iPad. Oh, that's cool. Yeah, if you want to ever send it that our way, if you want to say like, hey, Brian, check this out. Check out my Calc 3 stuff on Twitch. That's cool. No, I think Hold No Viewers was still really cool. I almost streamed the new Isaac. I was like, I should buy the new Isaac, Repentance. And I was like, I should just buy it and just like for April Fool's start streaming it. I had some ideas today. So Kayla and X are still here. I had this idea this morning. I was going to make a video. And the video I was going to put on it something like test 3 answers for TA use only. I was going to put like, I was going to upload that to YouTube. And I was like, what if people thought it was serious? Or what if like the university heard? And I'm like, it was an April Fool's joke. But the whole video, and I was like, well, I can't even use that. I was going to put something like that. And I was going to put a Rickroll in it. Like it would have like a picture of like the test or something as like the cover image for it. And then the video would just be like 5 seconds. And then it would just be like, do, and it'd be like a Rickroll. And I was like, I should have done that. But then I'm just like, what if the university here is like, Brian posted on his YouTube channel the test answers. And I'm like, it was an April Fool's joke. And then what if I get a DMCA claim for using the Rickroll music? I was just like, it'd be fun. See, what I could do is I could make, because people would see it's like an 8-second video. So I could make like a 12-minute video and then just put like a 5-second Rickroll at the start and just be like, test answers aren't here, April Fools, and just put the rest of the video like that as a blank screen, like just saying test answers here. Yeah. No, that'd make people too mad. I already did an April Fool's today where I, if you were in class today earlier, I did the April Fool's this way. And I'll send this out to the rest of the students, but I was like, I did this. I was like, I said there was a 2-point curve, and I was like, April Fools, and then I was like, oh, and I was like, not joking, and everyone was like, what? And then everyone got happy, and yeah. I think the guy might be calling here for whatever the interview is. Oh, what is this, Kayla? Thank you, Kayla. Oh, it's answers. Reasoning behind the names of trig functions, sine, secant, and tangent. The meanings of these words are very similar. The sine of an angle in the right triangle, the ratio, the opposite sides of the hypotenuse. The secant is the ratio. Yes. I will read up on this. It is Latin, it looks like. With that, I have to head off. Someone's supposed to be calling here soon. I will see everybody later. Bye for now. Thank you so much, Kayla. Thank you. That unit circle looks absolutely crazy right there. Bye for now, everyone. Bye.